Today we will learn about the case studies on critical infrastructure and urban risk. 5 cases from different countries are explained for this training, which are: Water Squares Project, Third City Western Sydney Designs, the Old City Centre of Faro, Portugal, Rapid Recovery System Case Study, L'Aquila Earthquake, Rebuild by Design. After case study demonstration, comparative insights about the cases were indicated. The learning objectives of the training are: distinguish between proactive disaster risk reduction (DRR) and reactive post-disaster softening (PDS). Evaluate how spatial redundancy enhance urban adaptive capacity. Assess urban vulnerability using both quantitative and qualitative methodologies. The Water Squares project illustrates the temporary use of space. These urban squares function as public spaces under normal conditions but transform into water storage facilities when it rains. Similarly, the floodable Eames Delta project reserved landscape areas for future changes, flooding, sea level rise, currently using the land for agriculture. This design approach falls under research focusing on enhancing adaptive capacity through design. This methodology challenges overarching frameworks like the Hyogo and Sendai frameworks, which are criticized for promoting post-disaster softening (PDS) rather than actual disaster risk reduction (DRR) through concrete spatial measures. The use of redundant space is tested against criteria for increasing spatial redundancy and closing environmental flows at a local scale. The water square enhances urban public space quality while storing water. One way to think of the water square is as a dual strategy. It increases the visibility and enjoyment of investments made in water storage facilities. Additionally, it creates opportunities to give local centers a sense of identity and environmental quality. The water square will be dry and used as a leisure area most of the time. From concept and idea to topologies, policy, and spatial design, it took 6 years. 3 basins are used to collect rainwater. One deeper basin only receives water when it constantly rains, while 2 shallow basins for the adjacent area receive water anytime it rains. Here, the water is gathered from the square's surrounding bigger area. Rainwater that falls on the square enters the basins through sizable gutters made of stainless steel. These locations are suitable for anyone on wheels and anyone who wishes to observe them in action while the weather is dry. The deep basin is both a theater to see and be seen and a real sports pit. Design-led research for the third city in Western Sydney applied principles of spatial redundancy. Designs like Ridge City shown in the visual propose concentrating density on ridges to create redundant space below that can accommodate climate impacts like floods or fires. This redundant space serves multiple uses, such as water treatment, recreation, or energy generation, only transforming into a hazard mitigation zone when necessary. These concepts emerged from 5 core design principles, including redundant space, consciously used temporarily, current use sacrificed when needed, and fluid densities, which can be increased or decreased over time. The designs demonstrate a shift towards spatial design rather than fuzzy policy planning. The third city in Western Sydney is a future urban development project, planned as the western city of the Sydney metropolitan area around the new Badgerys Creek Airport, and is anticipated to accommodate approximately 800,000 new inhabitants. This parkland landscape is highly vulnerable to future climate threats, specifically facing serious heat waves reaching up to 47 degrees Celsius and occasional flash flooding that can measure up to 9 meters. The design approach for the third city utilized research by design to explore spatial planning based on principles of redundancy and circularity, resulting in a model referred to as landscape-based urbanism. Designs resulting from this research propose concentrating high densities on ridges to create redundant space outside this elevated landscape. This redundant space is intentionally left free of fixed development so it can temporarily accommodate severe climate impacts like floods or fires. However, this land is not wasted. It is used for continuous activities such as wetland remediation, recreation, water treatment, enhancing biodiversity, or generating renewable energy from biocrops. The Old City Centre of Faro, Portugal, Ribeirinha area. This area, comprising 354 masonry buildings, was the focus of a large-scale assessment to evaluate the seismic vulnerability of its building stock. The study confirmed moderate to high values for the vulnerability of this specific area. Similar studies have been carried out for the old city centers of Seixal and Coimbra, Portugal. The core framework used is the Vulnerability Index-based methodology, classified as a hybrid technique. This approach calculates a Vulnerability Index score, IV, for each building based on 14 weighted parameters, P1 to P14, that evaluate aspects like the type of resisting system, number of floors, and conservation status. The methodology requires detailed inspection data but can use a complementary approach based on mean values for buildings with incomplete data. The seismic risk management procedure involves 5 tasks, starting with risk assessment. The FARO data was managed and analyzed spatially using a Geographical Information System (GIS) tool, ArcGIS 10.2. The Calculated Vulnerability Index (IV) is used alongside macro seismic intensity (IEMS-98) to predict mean damage grades (MUD) and generate comprehensive damage scenarios for different earthquake intensities, e.g., 8IX. The GIS integration allows technicians and decision-makers to gain a global view of the area, which is essential for planning interventions, accurate risk mitigation strategies, and emergency planning. The assessment framework further allows for detailed loss estimations, including the probability of collapsed, unusable buildings, human casualties, dead and severely injured, homelessness, and economic repair costs. The devastating L'Aquila earthquake highlighted the need for efficient logistical preparation by authorities for the temporary relocation of residents. This event stressed that planning for post-disaster recovery must value community engagement and decision-making, which is often neglected. The source positions this event as an example that should inform authorities on emergency strategies geared toward seismic risk. The goal of identifying vulnerable areas through seismic assessment, like in FARO, is to enhance both the response and recovery capacity needed after a disaster. The L'Aquila example is implicitly used to improve task, IV, implementation of the risk management program and V, monitoring of the results within the overall risk management process. This image shows the severe structural damage to a multi-story reinforced concrete apartment block in L'Aquila City. The visual focus is on a section where the mid-floor structure has experienced compression, leading to a crushing failure. This type of collapse was particularly tragic, as it illustrates the high vulnerability of the building stock, and in the specific case discussed, led to the deaths of 2 inhabitants who were trapped in a space compressed to barely 15 centimeters wide. Post-disaster mitigation, recovery action, buttressing. This image displays a severely damaged historical building in the center of L'Aquila City that has been extensively supported by temporary structural measures known as buttressing. The wooden, scaffolding, and electro-soldered steel buttresses are shown stabilizing the exterior of the structure, indicating they were designed to last for a very long time. It represents the immediate consequence of the disaster combined with the intermediate recovery phase, during which the Italian government organized a major buttressing program to hold the ruined historical urban fabric in place, even though the central area remained cordoned off and inaccessible to ordinary citizens for a long period. This buttressing is a hallmark of the extensive and costly, short-term interventions deployed by the national government. The Building Back Better (BBB) concept represents a transformative approach to disaster recovery, shifting the focus from mere restoration to systemic evolution. At its core, BBB posits that the period following a catastrophic disruption offers a unique window of opportunity to address underlying vulnerabilities that existed long before the crisis. Rather than replicating the flawed infrastructure of the past, this strategy integrates enhanced resilience, social equity, and environmental sustainability into the reconstruction process. A landmark application of this philosophy is the Rebuild by Design competition, initiated in the wake of Hurricane Sandy's devastation of New York City and the surrounding region. Moving beyond traditional top-down engineering, this process utilized an interdisciplinary model that paired global expertise with local community knowledge. The goal was not just to build walls, but to create resilient infrastructure that serves dual purposes, protecting the city from future storm surges while providing daily social and ecological benefits to residents. However, the BBB approach also highlights a temporal tension in urban planning. Because it is a post-disaster strategy, resilience is often born out of necessity following a tragedy. This emphasizes the importance of having flexible frameworks already in place so that when disaster strikes, the immediate pressure to return to normal does not override the opportunity to build a superior, more durable system. By leveraging the political will and financial influx that often follows a disaster, BBB transforms recovery into a proactive tool for long-term urban adaptation. Building back better has become a method for dealing with disasters, increasingly widespread after Hurricane Sandy. The BBB approach, which focuses on utilizing the recovery, rehabilitation, and reconstruction phases after a disaster to increase resilience, can be summarized across four key, interconnected elements. Equity and inclusion necessitate charting a course to ensure that no one is left behind, which involves identifying the needs and aspirations of marginalized groups and addressing vulnerabilities rooted in skewed allocations of resources, often through tailored support and meaningful participatory spaces. Integration and systems building underscore that BBB is a guided process where recovery assessments and comprehensive planning serve as the bedrock for programming, requiring a cross-sectoral view that corrects the persistent tendency to privilege physical reconstruction over livelihoods and social issues, ultimately embedding linkages to longer-term development goals. Knowledge, innovation, and technology are essential for making BBB safer and smarter by grounding reinforcement and re-siting decisions in a granular appreciation of spatial features and hazards, utilizing sophisticated tools like multi-hazard risk mapping, and blending modern advancements with local knowledge, such as traditional building methods. Finally, finance addresses the imperative of building back cost-effectively, demanding new methodologies to capture the costs and benefits of BBB solutions, particularly focusing on green infrastructure, which can be cost-effective in the immediate term, and structuring incentives to reorient funding mechanisms from simple replacement to robust improvement, despite the constraints of finite resources. To highlight how this approach started, it can be said that the design competition launched after Hurricane Sandy changed America's approach to disasters. The proposals put forward in this competition played an important role in the reconstruction of NYC. The greatest comparative insight lies in the philosophical distinction between preventing future harm and managing disruption after it occurs. To understand the three goals, disaster risk reduction, DRR, post-disaster softening, PDS, and risk assessment, represent distinct but often overlapping approaches to managing hazards, primarily differing in their temporal orientation and ultimate objective. Risk assessment acts as the foundational, preemptive step, involving activities like identifying existing fragilities and vulnerable areas, e.g., assessing the seismic vulnerability of old buildings in Faro, before an event to inform mitigation efforts and enhance response capacity. In contrast, DRR is a fundamentally proactive strategy, aiming to anticipate and accommodate future events, especially unprecedented or unknown ones, by implementing structural and non-structural measures, such as designing urban redundant spaces for floods or high-density areas on safe ridges. Finally, PDS, which includes the process of building back better, BBB, is inherently reactive, focusing on responding to disruption by reconfiguring systems to be more resilient after a disaster has struck, e.g., the reconstruction efforts after the L'Aquila earthquake or Hurricane Sandy. While risk assessment informs both DRR and PDS, the central comparative tension lies in the shift advocated by DRR proponents. Moving away from PDS, which proves the system failed initially, towards spatial and systemic planning that prevents disruption by leveraging imagination to anticipate the unknown future. A comprehensive strategy for managing disaster risk effectively must integrate pre-event assessment, proactive design, and robust logistical preparation across the entire timeline of disruption and recovery. This approach starts with rigorous risk assessment, emphasizing calculating the probability of damage and loss, such as estimating the mean damage grade, μD, or number of collapsed buildings, to acquire the necessary knowledge for planning effective post-event emergency responses. This crucial scientific analysis must directly inform proactive design strategies, exemplified by creating spatial redundancy and flexibility in advance, such as designing multi-purpose land or voids like water squares in Rotterdam or the unused landscape incorporated into Ridge City in western Sydney. These spatial planning interventions aim to increase resilience before or during disruption by accommodating sudden impacts like floods or fires. Finally, the strategy must include essential reactive measures, such as logistical preparation for temporary relocation of residents, a critical lesson learned from the L'Aquila earthquake, and planning for large-scale recovery efforts like the rebuild by design process established after Hurricane Sandy, thereby preparing the community for the lengthy rehabilitation and reconstruction phases. A critique for these approaches reveals fundamental limitations in current global frameworks and reactive strategies, particularly concerning proactive spatial measures and addressing underlying vulnerabilities. The practice of post-disaster softening (PDS), which encompasses efforts like building back better, is criticized because while it ultimately creates resilience down the line, it fundamentally proves the system was not resilient initially, as its focus is on recovery after a disaster has struck. This reactive stance challenges global frameworks like the Hyogo and Sendai frameworks for disaster risk reduction (DRR), which are argued to fail to deal with root causes of disaster and are criticized for placing excessive emphasis on PDS rather than concrete DRR through proactive spatial measures. Furthermore, this critique extends to the pre-disaster phase, where reliance on reactive measures often overlooks underlying threats. For example, in regions like Portugal, the evaluation of existing seismic vulnerability is frequently forgotten or undervalued due to the absence of recent significant seismic activity, leaving old, vulnerable building stock exposed to potentially disproportionately serious effects from moderate events. This pervasive lack of sustained interest and planning for risk reduction highlights the need for a conceptual shift away from mere softening towards strategies that anticipate and accommodate the unknown through imaginative design. The case studies use entirely different methods for deriving solutions and informing strategy, reflecting the nature of the hazard they address: quantitative, data-driven assessment, seismic design. The Faro case study is a rigorous, large-scale application of the vulnerability index-based methodology. This approach quantifies seismic risk as a convolution of hazard, vulnerability, and exposure, requires detailed, weighted scoring across 14 parameters focused on structural elements, resisting systems, connections, conservation status, produces quantifiable loss estimations, e.g., probability of building collapse, number of homeless, economic repair costs, that are directly mappable onto a GIS tool. Allows decision-makers to gain a global, statistically representative view of the vulnerability of the old masonry building stock. Qualitative, design-led inquiry, redundancy. The Third City Western Sydney case study uses research by design to generate innovative spatial proposals. This methodology involves deconstructing design principles from precedents, like Hafen City or Marrakesh, developing designs, Ridge City, Hydraulic City, based on core principles like fluid densities and integrated urban-rural water systems, testing the propositions against criteria focused on temporary use and closing environmental flows at a local scale. And the aim is not to calculate risk precisely, but to constantly adjust spatial configurations to accommodate a suddenly emerging context, leveraging imagination to anticipate the unknown. While focus of intervention can be compared with structure hardening versus systemic flexibility, the resulting mitigation strategies generated by these analyses target different aspects of the built environment, such as structural intervention, seismic design, in which the focus is on mitigating the physical vulnerability of existing, older masonry buildings. The high vulnerability confirmed in Faro leads to recommendations for structural interventions like retrofitting and strengthening actions, e.g., masonry consolidation, timber floor stiffening, effective connection between structural elements. The assessment specifically shows that poor maintenance and lack of adequate seismic retrofit often increase vulnerability. Another strategy is spatial, systemic intervention, redundancy. Its focus is on adapting the entire urban landscape system to manage climate impacts. Key strategies include land use that concentrating high densities on safe ridges to leave the rest of the landscape redundant space for floods or fires. Ecosystem integration to use redundant space for multiple continuous functions, such as water treatment, recreation, biodiversity enhancement, or energy generation, biocrops. Only transforming into a hazard mitigation zone when necessary. Flexibility to design spaces for multiple uses, like Rotterdam's water squares, suitable for accommodating rapid change, suddenism. In essence, the Faro seismic study provides a diagnostic tool for quantifying existing structural risk and prioritizing physical retrofitting, while the redundancy design studies offer a creative framework for spatially integrating resilience and flexibility into future urban planning. The comparative insight can be viewed through the lens of a house protecting its inhabitants. Seismic design focuses on reinforcing the walls and foundation to ensure the house resists shaking. Redundancy design, however, focuses on providing the house with floodable lawns and multi-purpose storage spaces, ensuring that even if the storm hits, the house and its yard can temporarily transform to absorb the shock and quickly return to normal use.